Theory. I only had 2 people do the extra credit problem at the back of the book. I was sort of surprised because I thought more of you might try to do that. It was not that difficult. Plus you had the answers in the back of the book. But anyway, that is what it is. So we're looking at decay chains. And we initially looked at if you have a number of atoms of A, they decay to B, they decay to C, where C is stable. This is a very simple problem. And you know the half-life's involved. You don't necessarily need to know the decay mechanism. The one they gave you in the book involved electron decay. So this was like 10 days for the half-life, and this was 30 hours. It went through and it looked at, just for a regular natural radioactive decay, if we look at the number of A's with respect to time, we have some initial number at time equal to 0, and it decays according to its decay constant. If we did a plot where we looked at number of A's with respect to time versus time, we know that it starts off at whatever this initial number is, instance 0, and then there's a natural radioactive decay. It looks like this, and this is the plot of this equation. This equation has 2 variables, N of A and T. And from just looking at this side, you know that T is the independent variable, N sub A is the dependent variable. So if I tell you a time, then you can calculate the number of atoms radioactively that remain at that particular time. We know that over time, all of A's will decay to B, and then over time, all of B's will decay to C, and that C is stable. If we look at what's happening with the number of atoms of B with respect to time, we know we can always look at what's happening with any type of function like this, is that if we look at this with respect to time, it is production minus loss. And where does production come from? The production is always from the decay of A's with respect to time. And what about the loss? The loss is the decay of B's with respect to time. If we can come up with expressions mathematically for these two, which we can, if we look at the rate of change of N of A with respect to time, we do this, then this is the loss of A's with respect to time, which is in fact becoming the production of B's with respect to time.
Professor, can you use a marker mark, please?
Say that again?
We can't see that marker.
Okay. What I'm showing here is I'm going to take, with respect to time, looking at this side, with respect to time, looking at that side, and this becomes the decay of A with respect to time. And we know the decay of A is the production of B. So when we do this mathematical function, we'll have the decay. And if we look at the decay of B, we know that that is decay of B is just its natural radioactive decay. If I substitute this into here, and then solve that, let me go back and see if I can get a better one here. And if you want to follow along on the textbook with this, they solve this to be equation 3-32, which is on page 60. But your final equation comes out to be NB as a function of time is equal to the decay constant of A times the number of original A's times lambda B minus lambda A times e to the minus lambda A of t minus e to the minus lambda B of t. And if we plot this equation, which again tells you n of B is a function only of time, time is the independent variable, n sub B is the dependent variable, the plot we have for that, it's going to start out at 0 because there are none of those. It will increase in value and then fall back off as already.
Excuse me?
Yes.
So
Can't see that here.
no, I can. It's so you said it was gonna be times e to the minus lambda A of t minus e to the lambda what?
B of t.
That's B of t, okay.
And again, this is exactly equation 3.32. So if I plot this equation, this is the plot of n of B as a function of time. We then know ultimately that all of the B's will go to C's. C is stable, so it's not decaying. So that's going to build up over time. If we look at C's, it's going to start down here at 0 because the time is equal to 0. Everything is just A's. And it's going to come up and eventually flatline out there, where the number of C's, as time goes towards infinity, is the exact number of A's that we had to start with. Knowing that, you can say that n sub 0 at any time is equal to the sum of A's with respect to time plus the number of B's with respect to time plus the number of C's with respect to time. This is a fixed number because that's the number of atoms that we started with. So we could find an equation for finding the number of C's with respect to time. Again, going back to production minus loss, the production would only come from B's. So if we went back and took the differential with respect to time, this is the rate of change of B's with time. So this is their loss, which ends up being the production of C's. Of course, C's has no loss because it's not radioactive. It's messy to solve it that way. If you come back here, you can see that n of C with respect to time is equal to the original number, whatever we had minus, by simply moving these two back to the left-hand side of the equation. So any time you can find the number of A's, number of B's, number of C's, you could also do it from looking at this plot. If we pick any particular time and we come up, we know we're going to have this number of A's excuse me, this number of B's, this number of A's, and this number of C's. And if we add this, we will get this total. Likewise, if we came out here at some particular time, that's the number of A's with respect to time. This is the number of B's with respect to time. This is the number of C's with respect to time. And if I add this and this to this, I'll come up with this total. So no matter where you are in time, you'll always have the original number of A's that you had to start with, but it will be a mixture of A's, B's, and C's until you get out to a longer period of time where everything will have gone from A's to B's, everything from B's to C's, so that all you have left are C's. If you had worked that problem 14 at the back of the textbook, that would have been working a problem just like this. I'm not really going to spend any more time on this unless you'd like to, although the quiz will be based on this type of problem. You think you understand the concept of decay chains and how you could calculate using this simplistic example from A's to B's, B's to C's with the function of time, as long as you knew the half-lives involved. Again, it does not make any difference what the particular item that you are generating, whether it be neutrons, protons, electrons, positrons.
Excuse me.
Yes.
I can't see that number of the half-life.
Okay. This one was 10 days, and this
Okay.
one was 30 hours, just to set that one up.
All right.
If we want to look at, for example, working a problem using just these numbers, we'll set this up very quickly. And let's say I had virtual number of atoms of A, let's say were equal to 2 times 10 to the 12th atoms. Okay. We know that the equation to look at the natural radioactive decay of A is this. If I plot this equation, it looks exactly like this black line. If I ask you to find the number of A's as a particular amount of time, and let's go with something like, what is T after time is equal to 4 days, how many A's do we have? So looking at this equation, we know the number of A's It's a function of time. In this particular case, it's 4 days. Is equal to the original number of A's that we had. Times e to the minus lambda A. And what is lambda A? Lambda A is the decay constant, but it's also 0.693 divided by the half-life of A. So in this particular case, move this up. This is going to be 0.693. The half-life is 10 days. And we want to know how many of these guys do we have after 4 days. So we're going to multiply this times 4 days. Cancel, cancel. So we have the number of A's.
What was the number on top?
Number on top is 0.693 divided by the half-life, which was 10 days.
Okay.
That is what lambda A is. So over here, we'd go out to wherever 4 days is. Find this point, plug this in, and that's the number of A's that we have at that particular time. So if anybody wants to do the math on that very quickly, so let me know what you get for N sub A, number of atoms after 4 days.
Sorry. What do you have times 4 on the side?
I'm taking my basic radioactive decay equation, where I know number of atoms of A, decay is a function of time. I have an initial number of atoms, and I know it decays according to this radioactive decay formula. And all I've done is substitute in values. I want to find out how many we have after 4 days. I know how many atoms we had to start with. And then I'm looking at the decay constant, which is defined here, times the amount of time we've had, which is 4 days. Anybody have a chance to work that value?
I got 1.52 times 10 to the 12.
Okay. Anybody else get that?
I got the same value.
Okay, thank you. So we'll assume that those two are correct. So after this amount of time, for number of A's, we have 1.52 times 10 to the 12th atoms. If we then look at B's, we know the number of B's